And really, the goal is to step away and go, you know what? Let me just ignore the science and just think. Fail back for some more MCAT podcasts, breaking down Blueprint MCAT Full Length 1. We're on passage 3. Any words of wisdom for students as they click that next button and go to that next passage to kind of like what I call like the Tiger Woods effect back when he was in his prime of being able to go, I just missed that drive, I just missed that putt, and then just move along and go, that's yesterday, today's today.
Yeah, I actually, during the exam, I do take a moment between, like, do like 2 passages, and then I just kind of like scrunch up my shoulders and hold my breath a little bit, and then it just kind of helps me like relax a little bit. And just like 3 or 4 seconds, just kind of like gets you in the zone. I think about how holding in that carbon dioxide acidifies the blood due to the bicarbonate blood buffer system, and then I like hop right back in.
Nerd. All right, so go hold your breath between passages. That's what Phil just said.
Yeah.
But do not inject disinfectants. That won't help.
No, probably not going to be beneficial.
And don't email me or post on social media. I know he didn't literally say that you should do that. Anyway, fun times on social media these days. Passage 3. Let's go ahead and dive in.
Yeah, looking forward to this one. Last time we talked a little about iodine and nuclear power plants and things like that. Now we're switching up. We're going to talk about Chanel number 5. I feel like if this was, if we could have timed this better, we should have had this come out on like Valentine's Day or something. It would have been the romantic Chanel passage.
Sure. Whatever you say. I don't think there's anything romantic about the MCAT, so.
Okay. We have different viewpoints then.
Which is why you tutor in it and I don't.
Right. I just eat, sleep, breathe MCAT. Exactly.
Mm-hmm. Right.
So the characteristic fragrance of Chanel number 5, one of the world's most well-known perfumes, is due almost wholly to 2-methyl-unduncanol, a compound found naturally in kumquats. The compound exists in 2 enantiomeric forms, figure 1, although professional perfumers note that the 2 enantiomers possess nearly identical scent profiles. So we have some structures here that give us the figure of 2-methyl-unduncanol. Note that it ends in al, which means it's an aldehyde. And looking at the structures, we can kind of like see these are going to be enantiomers. They tell us that in the passage as well. But enantiomers always have the same physical properties. They have the same boiling point. They have the same melting point, freezing point. They smell generally similar, although there are some weird stuff with that we won't go into. And so like if we're trying to like separate them, the MCAT likes to ask about like trying to separate aldehydes, or not aldehydes, but like enantiomers of each other, because kind of can't be done. And so you have to turn them into something that's not an enantiomer. So this is when everyone who's in organic chemistry right now is like, oh God, like I'm out, right? This is, I hate Orgo. So let's go ahead and jump back in. So we have a chemistry class conducted an experiment to separate 2-methyl-unduncanol from 2-methyl-unduncanoic acid by carrying out a distillation of a liquid consisting solely of these 2 components. Now, this is something that I think this is actually easier listening to me read this, because so many students, as they're reading this, are going to read like separate 2-methyl-unduncanol from 2-methyl-unduncanol because they talked about the 2 enantiomers. But now we're talking about the aldehyde from the carboxylic acid, which are not those enantiomers, right? They're bringing in a new kind of molecule here that they are not drawing. And so you have to be aware of that, especially when words just kind of turn into like one long list of like letters. Students just tend to like glaze over and they miss that second molecule is not the aldehyde form. So due to the high boiling points of these compounds, the class was instructed to carry out a vacuum distillation. Students began by placing 200 mils of the liquid mixture in a round bottom flask and adding several boiling chips. The solution was slowly heated with the distillate collected in the receiving flask. Students noted that the round bottom flask still held approximately 50 mils of liquid at the end of the distillation. And they give you the vacuum distillation setup, which is something that there's a good chance you have messed around with in Orgo lab back when people actually went to labs.
Back when I was a boy.
Yeah, we actually had to go into class to go to class.
Yeah. Okay. And so they have this drawing here with the round bottom flask and the tube connecting to the receiving flask and the vacuum hookup there as well. Okay.
Yeah. Something worth noting, they didn't tell us which. They said we were trying to separate the carboxylic acid and the aldehyde, and they didn't tell us which was left in the bottom of the flask and which one boiled off. They're absolutely going to ask this, right? And so trying to anticipate the questions as we're going along, there's going to be something about that for sure.
Okay.
Right.
So for a student to get into the right mindset. So I read this passage, or you read it, I'm listening to it, I'm reading along with you, and I go, I have no idea, right? I didn't pay attention in lab. I have no idea what they're going to ask. I forget all this stuff. How should a student progress forward into the questions after having completely given up reading the passage?
Well, it's worth noting that there's a lot of questions that are pseudo-discretes in the exam, meaning you don't actually need anything from the paragraph in order to answer the question. Yep. Even though this passage is obviously going kind of an organic chemistry route, Orgo is 5% of the entire exam, including the cars section of the psych-social. It's about 5% of the entire exam, which means it's not that common. And I find that the Orgo questions on the MCAT tend to actually be much easier than Orgo that you did in undergrad. They're not going to make you draw mechanisms, one, because it's multiple choice, and so you don't have to draw anything. But two, also, most of the questions in here are Orgo 1, just kind of knowing isomers or identifying is this a nucleophile or not, right? They're not going to ask you to draw the Wittig or the Clemmensen condensation or a Claisen reaction, Diels-Alder. They're not going to make you do all those things that you had to memorize to be able to regurgitate down onto a sheet of paper. And so generally, I tell students not to worry too much about Orgo unless they're missing questions. Okay. So I know a lot of students kind of have this idea that I feel like I need to study Orgo for 3 weeks before I can actually take an exam because I struggled with Orgo and I'm traumatized. But that it's better to actually take an exam, see what you struggle with in terms of Orgo, and then work on that specifically. But yeah, this passage is actually a pretty short one, right? It's just 2 paragraphs. Yep. There's not a lot of data in terms of tables and things like that. Basically, we just distilled this. There's not a lot for them to ask about. So I'm expecting a fair number of those pseudo-discrete questions asking us to, figure out the answer without really even needing the passage.
Okay. All right. Question 10. Which of the carbon or carbons in 2-methyl undecanal below is or are chiral? And so we have the same kind of drawing of this chemical structure from the passage, at least one of the enantiomers, and then we have a couple of the carbons labeled here, 1, 2, and 3. So good one to go check out the YouTube video for this one. So answer choice A is 1 only, B is 2 only, C is 1 and 2, and D is 2 and 3. So which of the carbon or carbons in this structure are chiral? And so the question for me is, number one, what does chiral mean? So if we got to start there, right? We have to know the definition of chiral. And I think chiral is where things rotate. Right?
Yeah, this handedness.
Yeah, and so that's how we get the enantiomers, I think. So where is this happening? And so I'm just going to look at the passage and go, okay, it showed me the 2 enantiomers below. Where are they rotated around? And it looks like they're rotated. So if you look at the one on top, the hydrogen is below. The one on the bottom, the hydrogen is above. Maybe, no. Yeah. So it obviously can't be all of them. So that one I'm going to throw out. So I go up over there. Oh, that's weird. Yeah. I don't know.
All right.
I don't know.
Throw a little bit of a bone here.
Yeah, no. Well, let me go back, right? So let me keep talking through this. So again, go to the YouTube channel, and you can see my mouse moving on this. Hopefully, is right off the bat, right? Again, if I'm talking like a complete noob that I don't know what I'm talking about, I'm just going to talk about what I see as different. So I have this CH3. I forget what we call that.
Methyl.
The methyl group. on the left here of this image, and we have the bond going up. But on the bottom one, the bond is going down. So right off the bat, things are already switched. And so do I need to take that into account as I'm looking at this? And I'm going to say no. Or yes, I do. And I'm just going to say, you know what? The methyl group and the hydrogen here are different, and is this alcohol, OH? This group is different as well. And so I'm just going to go, you know what? I'm wasting too much time. 1 and 2 I know are flipped, at least from here. I'm going to ignore everything else I see and go 1 and 2 only C.
Yeah. So chiral means it's attached to 4 different substituents. And so if you look at carbon 2, that's got this like methyl group sticking on it, the hydrogen. It's got this weird long chain, and then it's got the carbonyl on the other side. And so 2 is going to be a chiral center. 1, on the other hand, because of that double bond to oxygen, it's not connected to 4 different things. And so it's not going to be a chiral compound there. Okay. Now, here I'm going to do kind of like a high level, like extra bonus thing. I don't know why the MCAT does this, but they do this every time that I've seen so far. Like they may change this.
They do it every time they do it.
They every time they do it, they do it. They tend to leave in the dashes and wedges on drawings.
Yeah.
The only reason you would ever leave in a dash or a wedge is because it matters if it's coming towards you or away, and the only reason that would matter is if it was a chiral compound. And so even without like looking at like dashes, or even without looking at like finding 4 groups, like anything that's got a dash or a wedge attached to it is going to be a chiral compound. And that makes it quite a bit easier to answer a question like this. And there's going to be another question later on in this exam. I'm kind of like laying the trail of breadcrumbs. I think it's actually next week that this thing might be useful, that kind of like little clue to figure something out.
So potentially a little shortcut there, but maybe don't jump at that, but keep it in the front of your mind.
Yeah. Okay. That should be a good backup, like safety way to look at something.
So 2 only here.
Yep, 2 only.
Alrighty. Question 11.
The next question 11. Another possible method of separating 2-methyl-unduncanal and 2-methyl-unduncanoic acid could be based on. So we're trying to separate these. We did it with distillation in the passage. We're trying to find a different way to do this. Okay. So there are differences in the rotation of plane polarized light, which is A. B, a mass spectrometry analysis. C, an extraction based on their different solubilities. And then D, the very different scent profiles of each molecule.
And so the passage itself told me that the scent profiles weren't very different. And so I'm going to throw that one out, because I paid attention. Differences in the rotation of plane polarized light. And so the question is, I have to go back to organic chemistry or wherever this is and be like, are these enantiomers, do they do things differently with light? Is that a standard thing? And I'm like, something tells me it is, if I remember correctly, but I don't know. Mass spectrometry. Let me keep talking. Mass spectrometry analysis. It's interesting. So mass spec, I used to be like super... like I was a savant with mass spec. I could like see the thing and like draw it out in 2 minutes. And the professors are like, "Why are you cheating?" I'm like, "I'm not cheating." I don't know if chiral stuff would show because it's still the same makeup. So that one to me doesn't make sense. An extraction based on their differing solubilities. So is the solubility affected? So I'm left with A and C. So what were you going to throw at me after I mentioned the light stuff?
I was going to throw at you that you're doing the same thing that like most students do with this question. And they look at the question and they think that it's about the 2 figures that are drawn. This is not asking about the enantiomers. This is asking about the aldehyde versus the carboxylic acid. So it's not about the 2 images that are shown. Those are the enantiomeric forms. And so that's going to change some of your like thought process going through here. You're like, well, like the chirality is not going to affect this because the formula is going to be the same for the mass spec, but it's not the same formula. Okay. Because they're different molecules.
So is this a pseudo discrete then?
Yeah, I actually think this one is pretty pseudo-discrete. There's really nothing in the passage to help you with this other than just kind of like knowing like aldehydes and carboxylic acids.
Okay.
But yeah, do you have any like thought process on this? There's a couple of ways to kind of reason through this. But
I don't know if now you're like, okay, it's not the enantiomers, which is where my brain easily went to. It's this 2-methyl-undecanoyl and 2-methyl-undecanoic acid. I'm like, well, those must be two different compounds, and so the mass spec's going to be different. So I'm just going to jump right to that.
Yeah, and so the mass spec is going to be different for those. Enantiomers have differences in the way that they rotate light, and so a lot of students pick A because they're thinking about those enantiomers, but that's not what the question's asking about. I do like mass spec because that's going to show a difference between the two.
Yeah.
The extraction based on differing solubilities. So something that's more hydrophilic is going to go to the aqueous layer. Something that's more hydrophobic is going to go to the organic layer.
Let me stop you because something else that I don't think I really picked up on is the mass spec will tell you which one is which, but you can't separate, which is what the question is asking.
Absolutely.
So
that was going to be my takeaway at the end of like, here's a shortcut for this one. Like, it doesn't even matter what molecules they ask about.
Matter.
Only one of these.
Only one of these is separation, and that's the extraction.
Yeah. Right, it's the extraction. Like you can't like smell the bottle and like, ooh, now I've separated the molecules into two different containers, right? Like that doesn't make sense.
Yeah.
So
you go over there. There.
Exactly. Yeah, just kind of like wave the molecules one by one. So A, C, and D are all analytic techniques. B is actually the only separation technique of the ones given. But yeah, so the answer is C.
Answer choice C. All right. Critical thinking. Read the question, understand what it's asking, and apparently you get the question right most of the time that way.
Yeah, no, it's something they have to be kind of careful of. A lot of times students will read something and they will like immediately jump and like process and like they're trying to figure out like, what do I know about these things? And they bring up all of this stuff, but like sometimes you need to kind of like hold back. It's something I see a lot in the very smart students that really like problem solving. You ask them something and their initial response is to look inward and try to find like, use what I know to put stuff together. But that question, like really just which of these is separation? It doesn't even matter what the molecules are. And a lot of times people jump on the molecules, and even if they know what molecules they're doing, they're like thinking about those molecules rather than just like the easy way, which is like, which of these is a separation technique? That makes the question a lot easier.
Okay. Question 12. Boiling chips and vacuum distillation, respectively, are used in distillations to A, provide nucleation sites that give the liquid a place to start forming bubbles to prevent superheating, lower the boiling points of these substances to be distilled. B, lower the boiling points of the substances to be distilled, work synergistically with the vacuum system to further lower the boiling points. C, lower the boiling points of the substances to be distilled, and provide nucleation sites that give the liquid a place to start forming bubbles to prevent superheating. Or D, provide nucleation sites that give the liquid a place to start forming bubbles to prevent superheating. Speed up the distillation process by vacuuming the first distillate out of the apparatus. Okay, so boiling chips, you have to try to remember what boiling chips are. Boiling chips, I thought, provide nucleation sites. So if I go with that, I'm going to throw out B and C because these are saying that that boiling chips don't do that and that the vacuum distillation does do that. So I'm left with A and D. So hopefully right off the bat, I'm at 50-50. And so now the question is, because A and D both have the same first part, the second part is different. So vacuum distillation lowers the boiling points of the substances to be distilled, or vacuum distillation speeds up the distillation process by vacuuming the first distillate out of the apparatus. I don't know why it would speed up the distillation process by vacuuming the first. I'm going to go with A just because it seems to make more sense.
Yeah. And so vacuum distillation is a very interesting thing that boiling occurs when the vapor pressure of the liquid is equal to the atmospheric pressure around it.
If you
So
reduce
if you make
the
it
atmospheric pressure.
Yeah, if you reduce the atmospheric pressure, then it's going to boil at a lower temperature, which you have to worry about if you're cooking compared to if I was cooking. If you and I had a race to boil an egg, I'm going to win because you're at a higher altitude, and so you have a lower air pressure out there. And so as a result, your water is going to boil at a lower temperature, like 99 degrees Celsius instead of 100 degrees Celsius. So my boiling water is hotter than your boiling water. That's all I've got going. You got skiing, I've got warm boiling water. But yeah, and so also the boiling chips themselves just provide nucleation sites. The best example of this is Mentos.
Mentos, yeah.
You throw those in there, they produce nucleation sites where the carbon dioxide can latch and start to accumulate into bubbles, and then you get the big geyser of minty Coca-Cola. But yeah, so vacuum distillation lowers the boiling point. Boiling chips, they provide nucleation sites. Just to talk about why, because the MCAT might ask, why do you use and when do you use a vacuum distillation? If something's boiling point is really high, that's kind of fine, except for some molecules will start to break down at, let's say, 250 degrees Fahrenheit, and then they boil at 300 degrees Fahrenheit. And so if I tried to boil it, I'm going to break the molecules. And this happens with organic molecules. But if I can lower that boiling point down to 200 and the molecules break at 250, now it's going to boil off, and it's not going to break the molecules into chunks. And just kind of cause reactions to occur. So most of the time we see vacuum distillation with molecules that are organic in nature. It's just something that is likely to become reactive.
Yeah, and I just want to make a point here. It seems like a good place to make a point that I seem to be getting a lot of these questions right just from I don't want to say common sense, but just thinking logically through things. I don't remember any of this stuff, but a lot of it just seems like common sense. And I think where students potentially go wrong is not the lack of knowledge, which is where they always go to, and they put their head back in the book and try to learn more. And really the goal is to step away and go, you know what, let me just ignore the science and just think for a second about what is this asking about logically. What would a boiling chip do? I don't know what, but maybe logically, let me think through it. Right? Boiling chips, maybe I remembered from 20 something years ago that what it did, but more than likely I just said boiling chips, you know what? They probably provide a nucleation site.
Right. And that's the difference between the content and the application.
Yeah.
There's a lot of students that feel like their problem is content, and they need to go and study forever and that sort of thing. And I can't take a practice test until I've covered all the content, and then they take an exam and then they don't do well, because the MCAT is not going to ask you what's the definition of nucleation. Yeah. Right. They're not going to ask you for that.
Okay. All right. Question 13.
Is this one me?
Yep.
So the liquid remaining in the round bottom flask at the end of the procedure was most likely, this is the question we saw coming, right? It's a mixture consisting of roughly even amounts of the two components. B, 2-methyl-unduncanal. C, water condensed from the air in the lab. And D, 2-methyl-unduncanoic acid.
The liquid remaining in the round bottom flask. So that was the one that, if we go back to the passage quickly, had 200 milliliters of the liquid mixture. And the liquid mixture was both the 2-methyl-unduncanal and 2-methyl-unduncanoic acid. So the question is, what is left in there? And we're told that from the 200 mils initially put in, we have 50 milliliters left of something. So a mixture consisting of roughly even amounts of the two components. Again, not knowing anything, but knowing that this is an experiment that was set up to separate things. Why would we have equal amounts left of both? That just doesn't logically make sense. So I'm going to put that one on the back burner. B, 2-methyl-unduncanal. Okay, maybe because it's separated, right? So one of them is gone and one of them isn't. Water condensed from the air in the lab. Again, we're supposed to be separating things, so why would one of them go away and now all of a sudden we have water from the lab? That would hopefully wouldn't be a very good experiment. So again, logic, right? Just going, it just doesn't make sense. And so it would make sense that it's either one of the compounds. Now, the question is, what is, in my mind, the question is, what's going to boil off faster? The acid or the non-acid?
Mm-hmm.
And then I'm left with, again, going back to, I took this 20 years ago. I don't remember, but at least I got down to 50-50.
Yeah.
Right? And so I would probably, if I had to guess, say, maybe the acid boils faster because it's an acid, and I have no idea if that's right or not, but I'm just going to pick acid because I need to move on to another question, and hopefully I have a 50-50 shot.
Yeah, that's a really good thing to note, because that, like, just reasoning, like, some stuff just doesn't make sense. And it's very often you get to a 50-50 and then that last hurdle is like, oh, there's something I need to know for this. Right. And so in this case, we have the aldehyde versus the carboxylic acid. They're going to be very similar, except for the aldehyde is going to have this double bond O at the end. The carboxylic acid is going to have a double bond O with an OH at the end. The key there is that OH. So that OH is going to be able to hydrogen bond versus the aldehyde can't. And so that alcoholic group, the OH, is going to hydrogen bond with other molecules, which makes it stickier. And so it's going to stick to the other molecules. And so that's not going to boil as easily as the aldehyde, which is going to boil off a lot faster. Yep. So the one that's left in the container is going to be the carboxylic acid because of its ability to hydrogen bond, because it's got that alcoholic group.
So it's funny. That's the answer that I picked, because in my head, as I was talking through it, I forgot what the question was. And so I answered the question, which one's going to boil off, because that's how I was rationalizing it. And that ended up being the right answer, even though I should have picked the other one. So again, thought process, and you're seeing mistakes that students are making as they're thinking through the process. They're changing the question in their head and they pick the wrong one. And they go, oh, that's why I missed that one. I thought about it wrong.
Yeah, and that's, I think, the second one for this passage, where it's like, oh, I need to make sure I'm answering the question, right? Like, what is the question that they're actually asking? And this is something that, like, this sounds like a really obvious thing, but when you're in the zone, you're kind of like thinking about it, especially because the exam normally is like 7.5 hours long. Now it's a little bit shorter for this upcoming round. But, like, you know, if you're sitting there working for 5 hours or 5.5 hours, it's really easy to, you know, get a little fatigued, to make those little silly errors. But yeah, that generally happens with students the first couple of exams they take, and then later on they're kind of like kicking themselves and they've built up enough stamina. They're like, I need to make sure I answer the question and stick to it. But yeah. So the answer for that one is the 2-methyl undunquenoic acid.